Okay, yesterday we started looking at how you fill electrons into these orbitals that Schrodinger gave us for their energy states. Um, so we started out by realizing that the orbitals are all a jumbled mess, and I guess I'll show you the picture there. And so we use the diagonal rule to help us remember the order in which they're filled. And that diagonal rule, well, we saw that yesterday. Um, so the we then had said there's three rules to follow. The first rule is the Aufbau principle. That means basically start at the bottom, fill it up, work your way up to the top, fill the next one, the next, and the next, so on, following the diagonal rule of the jumbled mess up there. So again, Aufbau means build up. Start from the bottom and fill that 1s orbital, then fill 2s, then fill the 2p orbitals, and so on. So we build up from there. But how do you know it's full? Well, that's where the second rule comes into play, and that's the Pauli exclusion principle. Okay, the Pauli exclusion principle limits us to one electron with each spin state in each orbital. So bottom line is 2 electrons per orbital. And so that 1s orbital can hold 2 electrons, as long as they have opposite spins. So that's what they show here. In the next slide, they talk about spinning clockwise or counterclockwise, but the magnetic field then points up or down, and so we talk about an electron being spin up or spin down. Okay, so in that level 1s electron or 1s orbital, you could put an electron that spin up, you put a second electron that spin down, but a third electron would have to repeat one of those 2 spin states, and you can't double up 2 spin ups or 2 spin downs. The reason why, by the way, is the magnetic fields would repel each other, for those of you interested in that kind of thing. So, notice within an orbital, that little box they show that fits the electrons in, you can fill it up like this, putting one electron spin up, the other electron spin down, the orbital is full. And now you'd have to move up to the next orbital. Okay, so that's that. We're going to leave the PowerPoint behind, and I'm going to start filling this in. Now, let's again do Aufbau. We'll start with the simplest atom of all, and that's hydrogen. There's one lousy electron in there. So where is that one electron going to go? It has all these energy states to go into. Well, it chooses to go into the lowest possible energy state. And that is right here in level 1s. So again, I draw an arrow pointing up. When we do it by hand, we usually just draw a half arrow. Now, that means you have one electron in the 1s state. And drawing this whole diagram is a little much for that, isn't it? So often what we'll do is we'll use a shorthand for this. And that shorthand is called an electron configuration. Okay, how we show it is, now for hydrogen, it's just that one electron that you can see up there. You say it's 1s, that's the level and sublevel you have, and then there's one electron in there. So you put that 1 as a superscript up here. Now, I know it looks like an exponent, 1s to the first power. In quantum mechanics, you don't read it that way. You read it 1s1. What it means is there's orbital 1s, and it contains one electron within it. Okay? So writing it that way is shorter than drawing out all the stupid arrows. Well, it's only one arrow here, but still, it's shorter than drawing the arrow. Okay? So we will often do electron configurations to show us in a shorthand way. Oh. Okay, it's working. We use electron configurations to show us in a shorthand way what the arrow diagrams are looking like. Now, what if I go to the helium atom? Okay, helium atom has 2 electrons. Where do they go? Well, the first electron, we already know where it goes because we put it in there for hydrogen. The second electron, well, it's lazy. It wants to go in the lowest energy state possible. So it wants to go in level 1s. Can it go in there? Sure. There's only one electron. There's room for 2. So that second electron for helium is going to go right down here. Oops. I gotta make my brush come back. It's going to go right in here, and you have 1s with 2 electrons in now. Notice one of those electrons is spin up, the other electron is spin down. So, scrolling down here, I can write the configuration for the helium atom as 1s2. Okay, so you see how, again, it shows there's level 1s, and now there's 2 electrons in there. Now, notice we are using a shorthand way of showing this. Again, it's easier than drawing the box with the arrows in it. But whenever you shorten something up, you eliminate parts of it. You lose some information. In this case, we're losing the spin information. So when I write for hydrogen 1s1, that's fine, but is that one electron spin up or spin down? Don't know. It doesn't tell you that. Luckily, the hydrogen atom doesn't really care. Presumably half the hydrogens in the universe have their electrons spin up and the other half have them spin down. But they're tumbling through space anyway, so it doesn't really matter. So we lose information that doesn't really affect anything anyway. Now, with helium 1s2, okay, great. We know we have 2 electrons in there because 2 electrons can fit. But when you draw the arrow diagram, you can clearly see that one is spin up and the other is spin down. They are spin coupled, or they're paired up. And that's what they have to be. You cannot put them in there both the same spin. It would be inappropriate to put the 2 electrons in there, one spin up and the other spin up also. Never ever do that. Okay, they got to be opposite spin states. Now, when you look at the arrow diagram, it shows that very clearly, that they're opposite spin states. Well, with better handwriting, it shows it clearly anyway. When you do the shorthand way of writing it, the electron configuration, we write 1s2, and no one can see those spin states. So, we're putting more pressure on our audience. When I write 1s2, my audience needs to understand that I mean those 2 electrons are opposite spin states. They are spin coupled. They're not the same spin. Okay? Eventually that becomes important. Now, again, that information is not shown here. That information is now just placed on the audience that they have to just understand it and know it. Of course, I guess if someone didn't know that the electrons have opposite spin states, they have no business looking at electron configurations anyway, right? So, let's move on and go to element number 3, which is lithium. Okay, now there's 3 electrons. We already know where the first 2 go. The first one goes here, the second one goes there. What about the third one? Notice we're aufbauing, we're building up, right? Where does the third electron go? Well, it would love to go here in level 1s. It's, the lowest energy. It's lazy. But it's full. So now that third electron's got to go up here in 2s. And there it is. So the configuration for lithium, we would write 1s2, 2s1. Okay? Because there's 2... I keep losing my cursor. There's 2 electrons down here in 1s, so that's the 1s2. And then there's 1 electron up here in 2s. That's the 2s1. Okay? So you can see it's going to start getting cumbersome as we go up to level 4 and 5 and so on. But let's continue on. Element number 4, which is beryllium. Well, yeah, you're going to pair it up and go 1s2, 2s2. Now, the next element, boron, there's 5 electrons. Well, we got 4 already. Where does the 5th one go? Well, it's going to go up here in 2p. But which 2p orbital does it go in? You got a choice now. You never had a choice before. Well, it doesn't matter. They're all exactly the same energy. So you put it in any one you want. We usually start from the left to the right the way we normally write things, but it wouldn't really matter. You put it anywhere. I'm going to put it right here in that orbital. How would you write that? 1s2, 2s2, 2p1. Okay? But now when we go to the next element, carbon, now suddenly we have another choice we didn't have before. You got your 2p1. Carbon's going to have 1 more electron, making it 2p2, right? So you'll have 1s2, 2s2, 2p2. Total of 6 electrons, 2, 4, 6. But now, where does it go, that last electron? Yeah, it's going to go in 2p. But does it go in here and pair up with this guy? Or does it take its own dorm room, go into a different orbital completely? Well, what would you do? You're going off to college, you got a choice. You got to cram into a dorm with someone you don't know, or you get your own private room. Okay? Electrons are going to take their own private room. And so that second electron is going to go here. Okay? Now again, writing the electron configuration, we don't see that information. We just see 2p2. It's on our audience to understand that those p electrons are unpaired. Notice not only are they unpaired, but they also have the exact same spin state. They're both spin up. That's important also. Now, the guy who first figured that out was a German guy named Hund. So we call this Hund's rule. Okay? If you have a choice of where to put the electrons, up until now we didn't because s orbitals, there's only one of them. So you're in an s orbital, you put the electron in the s orbital. There's no other choice. But when you get to p orbitals, suddenly you have a choice because there's 3 different p orbitals. Hund's rule says electrons will go into separate orbitals with the same spin state as much as they possibly can. So I showed you carbon having 2 of them, put this one, that one was empty. Here in the PowerPoint, they're showing you 3 electrons, 1, 2, 3, which would be nitrogen, the next element on the periodic table. You split the electrons up as much as you possibly can, and you give them the same exact spin state, all spin up or all spin down, your choice. What happens if I have a 4th electron, if I go to oxygen? Well, it would love if there were another orbital over here, but there isn't. So it's going to have to start pairing up now. Okay? And let's see here. I want to scroll down and see what they say about that. Yeah, they show it right here. If you have another electron, a 4th one, now it has to start pairing up. All right, so let me come back to my drawing here. This is carbon, 2p2. The next element, nitrogen, 2p3. Oxygen, 2p4. And don't forget 1s2, 2s2, 2p4. They're all there. Now fluorine, 2p5. And neon, 2p6. Notice the noble gas neon has a full shell. If you think back, 1s2, there is no 1p, so 1s2 is a full shell. That was helium, another noble gas. The noble gases are noble because they end up with those s2p6 full shell configurations. Okay, so you're going to find every single noble gas ends up with filling the shell. Okay, now after neon, now we go to sodium, 3s1, and then 3s2, 3p1, 3p2, 3p3, that would be phosphorus if you look on your periodic table. And then 3p4, 3p5, 3p6. That's argon, the next noble gas. So to write it all out, I guess, we'd have to write all of these. 1s2, 2s2, 2p6, 3s2, 3p6. Now, after that, then again, that's the noble gas, argon. After that, where does the next electron go? If I go to potassium, you're real tempted to put it after 3p, go right, I keep losing my cursor. You're real tempted to put it into 3d right here. But remember, they get jumbled up. Take a look back at your diagonal rule. The next one it goes into is 4s. Okay? And so, oops, I didn't want to do that. Well, it goes into 4s as the next one. So, if I want to write that whole configuration out for potassium, I'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And that's going to be potassium's configuration. Now, the next element would go 4s2, and that's what's after potassium, calcium. And now finally we go back and start filling in 3D for scandium, titanium, vanadium, chromium, and manganese. Now after that, we can come back to iron and start pairing them up. Notice again, the d orbitals follow Hund's rule. Okay, this might be easier to follow if you're actually looking at a periodic table while you're doing it. Looks like I have like less than 10 seconds left, so I'm going to wrap it up here, and then we'll continue on this tomorrow.